Good afternoon, everyone. It is my pleasure to introduce today's speaker, Professor Eva Laplace. If you're wondering about her name, the origins are German and French, right? And Eva started her scientific career doing X-ray astronomy in her bachelor's and master's, and then moving to stellar astrophysics for her PhD in Amsterdam. After that, she did a postdoc in Heidelberg, and is now a Venny Fellow at the University of Amsterdam and an assistant professor at KU Leuven. In addition to her scientific work, Eva has also led a team that developed a game called Habitable, which is a game about habitability of planets and our planet. And this has won an Outreach award from the German Ministry of Education and Research. And she has also won an Outreach award from the Dutch Royal Society of Science and Humanities for Tulips, which is a visualization tool for stellar astrophysics. I'm sure we'll see some images using that. And now she works on massive stars, gravitational wave progenitors, and some other things that we'll hear about. Eva?
Hello, everyone. Thank you very much for this invitation. It's been a great pleasure for me to be here in Cambridge and to meet many of you and to talk to all of you. And so today I'm very excited to tell you about my recent research that of course has been done in collaboration with many people, the main ones being listed here, but I have also many other collaborators. And so what I'd like to tell you about today is the effect of binary mass transfer on the evolution, the fate of stars, and also their afterlives, because this is a really exciting time. So, as you all know, before something like a decade ago, this was basically the whole picture of what we knew about compact objects. In red, the known black holes, mainly from X-ray studies, and in yellow, the neutron stars. And we are, of course, experiencing a revolution thanks to the observation of gravitational waves. They have completely changed our picture of what stars look like at the end of their lives and in their afterlives. And so this is incredibly exciting because we can finally learn about some of the unknown aspects of stellar evolution. And we can measure it, we can actually see what nature does. And we can already identify some very interesting structure in the first published data of LIGO, Virgo, and other observatories. And of course, we're all waiting for the end of this summer when we're supposed to have basically double the amount of compact objects thanks to the next data release. And so something I'd like to point out here as someone who thinks about the theory of stellar evolution is the kind of patterns we can already observe here. And so one thing that many people are excited about is this potential mass gap between the lowest mass black holes and the highest mass neutron stars. There is some evidence that there is a dearth of objects in this gap. But we have already found some objects there too, which is very exciting because it tells us something about how black holes form and how much matter they accrete when they form. Additionally, something very interesting, one of the most robust predictions of stellar evolution is that there should be a mass gap also on this higher mass end. And that is connected to these pair instability supernovae, so supernovae of very, very massive stars. Interestingly enough, we don't seem to find it. It's strange. So there are many puzzles here, and with more and more observations, we will be able to learn even more about compact objects and how they relate to the stars that form them. And something I'd like to point out is that we not only have a revolution in the terms of gravitational waves, we can also see many more compact objects, in particular black holes, thanks to ongoing efforts to measure the positions of stars. So thanks to Gaia and thanks to many surveys of massive stars, we actually know even more black holes in our nearby universe. And it's incredibly exciting. And the Gaia collaboration has also released already early on now the discovery of this 30 solar mass black hole that was so obvious in their data that they already released it early. And there are many more to be expected in the next data release, where we will see also the more massive end of the spectrum. So this is a really exciting time to be working on black holes and the stars that form them, which is what I'm going to tell you about today. Another thing I'd like you to observe here is what I find very intriguing, is that basically most of the black holes that we've observed nearby that are consistent with coming from solar metallicity align at a mass of around 9 solar masses. This is very interesting. And if we look at the whole spectrum of the mass distribution of gravitational wave sources, so in terms of their chirp mass, so that's a combination of the masses of both compact objects that merge. Here we're looking only at binary black holes. Then you can see even more structure. People have identified a number of features, so that I pointed out by the blue arrows here. And some of them are statistically significant. For some of them, we'll have to wait for the next data release to tell us if they're real or not. But there's a consensus that there is a peak at around 8 or so solar masses in terms of chirp mass. And that is the most prominent peak. That's the most common black holes that should have been observed. And there is another peak at around 30 solar masses in terms of chirp mass. That is very puzzling, because we don't really know which stars form these black holes. And then there might be some other peaks and potentially a gap that is highlighted here between 9 and about 12 solar masses. Strange and interesting, and something I will connect to during my talk. So this is something to keep in mind. And now I'm going to first talk you through a little bit of binary evolution before coming back to black holes. Binaries. Okay, so binaries are a very exciting subject because they are also one of the main new findings in stellar evolution in recent years. So while before there was this beautiful theory developed about single star evolution, we actually know now that most stars live in binaries, and basically all massive stars live in binaries. 80% of them live in such close binaries that they will interact during their lifetime. And today the binary products I would be focusing on are the binary strip stars. What are these stars? These are the stars that are the initial donors in these systems. So the bigger one on this picture, that will lose its outer layers by transferring mass to the companion star and become what we call binary stripped. Why are they interesting? Well, they're incredibly common. They're like the most common type of common outcome of binary mass transfer, like 30%. They can be modeled reasonably reliably with stellar evolution code, and they're also very important when it comes to gravitational wave sources. Why is that? If we look at the whole process of binary evolution that you need to take to get from two stars that live together, so that's called isolated binary evolution, to the formation of a double compact object, for example, two black holes that will form within the age of the universe, there is a whole lot of processes going on, okay? But I just want you to focus on two things, and these are highlighted with these purple boxes here, and these are the phases in which stars actually form black holes. And this is a standard outcome of anyone who has looked at this problem. It's very interesting, but the star that forms the black hole is always a strip star. Always a strip star, okay? So we really need to understand these strip stars better. And this is why they're important in the context of gravitational wave sources. So let's talk about the impact of binary mass transfer, just for a minute to really understand what it does to stars. So on this plot, we have an HR diagram where we see the typical evolution of a single star of about 10 solar masses, shown in gray. It evolves like a typical single star and will, at the end of its life, explode as a red supergiant, and basically only evolve towards the right side of the HR diagram. Now, if we take exactly the same star and put it next to another star in an orbit that is close enough that they will interact within their lifetime, this is what's going to happen, and it's shown in purple here. So there will be a phase, intense phase of binary mass transfer, where there will be a dramatic change in the structure of this star that becomes a stripped star. It fills its Roche lobe, it dumps a lot of material on the companion star, and as it loses these outer layers of hydrogen, it becomes very small, very compact, very, very hot. And essentially, it was invisible for many years, but it was a standard prediction from cell evolution for many, many years, and they finally have been discovered. So this is a very recent discovery of the last 2 years. In the last 2 years, we finally have found the missing strip stars. These were predicted for a long time, but basically because these stars are so tiny and they mainly shine in the UV, they were missed before, and now we can see them. And we also, in the search of black holes, have found stars that are called partially stripped at the same time. That's sometimes masquerade as stars that could be black holes. So we are in a time and age where we can actually constrain all these properties of binary evolution thanks to observations with strip stars. And so this is not the end of the evolution of such strip stars. It's just a very long-lived phase of core helium burning, at this point 3 I was highlighting. After that, there's still a phase of evolution when the stars burn helium in a shell, and then all the other cycles of nuclear burning, and then explode as supernovae. So this was exactly the same star. But if it's in a binary, it will have a completely different life, and also a completely different death. I'll come to that in a moment. So I think Avishai is one of the few people who has actually gone through the effort of actually trying to model a population of binaries and to see what their endpoints are. And you can see, this just to give you an overview, that there is an incredible diversity in the progenitors of supernovae and of black holes when you consider these binary effects. And it looks a little bit random here, but there's actually some structure to this, and that makes it also very interesting, because we can start to look for stars that potentially going to form a black hole tomorrow, or going to explode tomorrow, which is a shared dream. It would be fun. Okay, so what we've learned so far is that binary mass transfer really affects the life and the death of stars. But this raises a question. We have only looked at the outer layers of stars, basically, and we've seen that this changes. But what happens to their cores? Does that matter? Does binary mass transfer matter for the stellar cores? Well, it turns out that it really does. And this has a number of really exciting consequences. So if you look at the typical structure of nuclear burning inside a star, of a single star, shown in this visualization on the left, and of a star that has basically the same core mass, but was stripped during its lifetime. If you compare them, just visually, you can tell that they have a different nuclear burning structure. Why does this matter? Well, this matters because this nuclear burning structure basically tells you something about the density and the temperature distribution inside a star. And this tells us also about the fate of such stars. And this also translates in a difference in composition of these stars. So if we take a single star or a binary strip star, and they have the same core mass, and we look at what they are made of which is shown here in this composition diagram, which is essentially a pie chart where for each layer in the core of a star, you can see which element it's made of. So in the outer layers, this helium core, the star is made of helium and a bit of carbon and nitrogen. And then inside there is this oxygen, neon, magnesium core, and inside what we like to call iron, but of course it's just a bunch of iron group elements. And when you compare it to the binary strip star, you can see that the composition is slightly different. We have a pocket of carbon and oxygen and nitrogen around the inner oxygen, neon, magnesium core that is absent in the single stars. And this doesn't look like much. But it actually really matters for what kind of elements are ejected from such a star into its surroundings during its lifetime. And so we have made some calculations about this with a colleague of mine, Rob Farmer, and then with a student of his, Jingze Ma. And what we found initially was really exciting, and that is that strip stars are really much better at producing carbon in the universe compared to single stars. Carbon, which is the building block of life, right? Every organic molecule is based on carbon. And so this was very, very exciting. And then we looked at it a little bit more carefully. And recently we've published something about this. Well, we put it on the archive at least. We looked at this in terms of metallicity. And it turns out that this is a little bit sensitive to the metallicity of the star. This has to do with the mass loss that stars experience during their lifetime and how that affects the core structure of stars. And so this study is a little bit limited in the sense that at lower metallicity, we actually know that stars will go through several phases of mass transfer. And here we only modeled one. So if we only model one, it looks like these stars at lower metallicity will enrich the universe a little bit less in carbon. But to really know what happens, we would need to take all these phases of mass transfer into account. But because I know that lots of people work on chemically peculiar stars, I thought I'd mention also that we looked at actually the whole spectrum of what kind of elements could be produced in such strip stars at solar metallicity. And there we found some really fun patterns. So when we compared the total yields of these stars, we could actually find that binary strip stars are really good at making potassium, which is quite interesting because that might be related or connected to some of these unusual potassium abundances that people have found. We don't really know, but this is a channel that I think has not been thought about too much so far when it comes to chemically peculiar stars. So binaries can also contribute to there. Takeaway point here is that binary stripping really affects also the deep interior of stars and their composition and the nuclear synthesis, what kind of elements they eject into their surroundings. But what about their afterlives? What about the compact objects, which I was motivating this talk with? So we have typically this picture that is taught in like basic astronomy classes because it's a simple way to think about the fate of stars. So this picture is that low to average mass stars, when they end their lives, will all form white dwarfs. Then if you increase in mass, all of them will explode and form a neutron star. And when you go to even higher masses, what is going to happen is that all of them form black holes. Okay. And so the fate of a star is only dependent on its initial mass and nothing else happens, and that's it. That is the kind of assumption that has been put in many, many descriptions of galaxy evolution, supernovae, etc. But it is vastly oversimplified. So this is also something I'd like to tell you today. Actually, whether a star forms a black hole or explodes or forms a neutron star, these are actually quite complicated questions. And this has been known for a while, actually. So 30 years ago, there were already some studies on the final iron core masses of stars. Why does this matter? This matters because when a star forms an iron-rich core, it will actually reach a state where it will no longer be able to sustain enough energy through nuclear burning to counter the gravitational collapse. And so this is usually what triggers the collapse of the core. So looking at this iron core mass, if it's above a certain limit that we call the effective Chandrasekhar limit, then you would expect that it collapses and forms and triggers potentially an explosion or forms a black hole. So if we look at this plot from 30 years ago, what people found is that if you look at the iron core mass of stars as a function of the initial mass of a star, well, it doesn't look very linear, does it? Right? So it's not like when you go to much higher masses, you will immediately have stars that will all have very high, large iron cores that will be able to collapse and form a black hole. It looks a little bit more complicated than that. So what happens if you take like latest stellar evolution codes and with the latest physics input and you try to do the same exercise? Well, we find basically the same thing. And that's very interesting. So the final structure of stars, in terms of their iron core mass, but you can use many equivalent quantities as a function of their initial core mass or their initial mass, is actually strongly non-monotonic. So you can't just say, okay, all massive stars form black holes. It's more complicated than that. And so, yeah, as I mentioned before, this really matters because this will tell you whether a star will actually collapse and whether it will form a black hole or not. So this is also connected to the supernova mechanism, how stars explode, etc., which is a very complicated problem. But if we just look at this from a stellar evolution perspective, and we simply make this connection between stars having large iron cores being very tightly bound, that means that if they have a large iron core mass, they will be quite difficult to take apart, to explode. Okay, so if we have a peak in iron core mass, we would expect that a star would form a black hole. Okay? And so people have tried to find summarizing quantities to describe this. And one of these quantities that has been discussed in the literature and that I think Evan O'Connor, who was visiting here, has probably told you about is this compactness parameter that I think he introduced. And basically the idea is if you are above this critical line, stars will be more prone to forming black holes, and if you're below this line, they will be more prone to exploding. And then potentially they form neutron stars, potentially they form black holes. This is also a difficult question. But the takeaway point is if you're above this line, you will most likely form a black hole. And so the interesting thing is that literally everyone who has looked at this problem has found the same pattern. So people with different stellar evolution codes, people who have made different assumptions concerning the microphysics, but even the nuclear physics, everyone finds the same pattern. So that means that there is some underlying, same underlying mechanism. So it is the same qualitative pattern, so that you have these peaks in compactness or iron core mass, but it's not the same quantitative pattern, yes? So if you change the microphysics, you will find different outcomes. And why are people excited about this? Well, one of the reasons is if you turn this compactness into a prediction of whether stars explode or form black holes, as shown on this HR diagram, then stars will, I hope you can see, yes, stars will tend to explode first, then they reach this peak in iron core mass or compactness and then form black holes. Then they explode again and then they form black holes again, okay? And the fun thing is, one of our best candidates for a disappearing star was found exactly here, which is exactly the place where we expect this compactness peak to lie. Unfortunately, it's a very contested observation because there have been new JWST observations of this potentially disappearing star that has not reappeared. And there seem to be some sources at this location in the infrared. So we don't really know what this is, if this is actually a surviving accreting black hole, or if it wasn't a disappearing star that formed a black hole in the first place is unclear. But yeah, anyway, these are the kind of predictions you can get from this compactness. So we looked at this problem to try to understand where this pattern actually comes from. Which are the stars that are prone to forming black holes? And it took 3 years, but I'm happy to report that we actually think we understand why. And this has all to do with the evolution of massive stars. So there's a very fun thing that happens in massive stars, and that is that after core helium burning, what actually dominates the final evolution of the star is a spontaneous process called thermal neutrino emission. And that is because the temperature and the density is so incredibly high in these stars towards the end of their lives, they can spontaneously produce neutrinos, right? In particular through this process called pair annihilation. And what this means is that stars, massive stars, experience a net energy loss at the end of their lives, right? Because these neutrinos are these tiny particles that have such a small cross-section, they will basically not interact with anything and just go away, and then you have a net energy loss. What does that mean? The evolution of massive stars is vastly accelerated. So you will have all these phases of contraction, expansion, etc. will be vastly accelerated at the end of the evolution because the luminosity from neutrinos actually even exceeds the luminosity of the star. And so what determines the final fate of a star, whether it will be able to form a large iron core, will be determined both by the phases of nuclear burning at the center and also by how many neutrino losses this star experiences. So to give you some ideas, so this is basically dependent on the rate of nuclear burning, which is set by the density and the temperature of the star, so something like the mass, but also by how much fuel the star has at that time. And how much energy it loses is also determined basically by the density and the temperature of the star. So if we look at the balance between these two, and we look at the succession of nuclear burning episodes and the effect of neutrinos on nuclear burning, we can try to understand what happens at the end of the life of massive stars. And just to keep it short, I just have a summary of our findings here for what this means for these peaks in compactness or iron core mass. And what we found is actually really interesting. So it turns out that for these massive stars, when you have a certain core mass, when you go to higher core masses, you actually start to have less fuel at the center. And what that means is that the rate of neutrino losses goes up. And it goes up so much that even the nuclear burning is dominated by neutrino losses. What that means is the star will lose a lot of energy and will have to contract more. So we will see this compactness of the star go up, and the star will be able to form a larger iron core. But then this process becomes so extreme that we will have such a fast contraction that you can actually ignite the next burning fuel earlier. And that again stops the contraction if you go to higher masses. So in this, with this process, we can explain these peaks in the compactness of stars. And the fun thing is, exactly the same process also happens at higher masses, but then it involves the burning of neon instead of carbon, and then it is stopped by the next stage. So just as a takeaway, basically we can explain just from stellar physics why some stars will form these larger iron core masses and will be prone to forming black holes. And this is fun because it gives us a prediction from stellar physics telling us whether stars will form black holes or not. And here is where I come back to binaries. Why does this matter? Because I told you before that the cores of binaries are different compared to single stars, right? And so what we find is that also where this compactness happens, where stars are prone to form black holes, is shifted in binaries compared to single stars. And we see that this has vast consequences. So basically, the stars that will form black holes will be different in binaries compared to single stars. And this is something we usually don't consider much. So if we look at the masses of black holes that you expect when stars are these binary strip stars shown in orange here, in terms of their initial mass, and here in terms of their final compact object mass, and we compare it to single stars, we can see that they have very different outcomes, right? Like at very high masses, these strip stars will sometimes not be able to form black holes because they will not have these islands of black hole formation at the same place. And the main difference comes from the fact that they have lost their outer layers. So these strip stars will also tend to form much smaller mass black holes, right? They will tend to form black holes of about 9 solar masses. And then again, at the higher mass end, while for the single stars, they will be able to form a whole range of massive black holes because they retain their big hydrogen-rich envelopes. So the takeaway point here, I hope this was not too technical, is that black hole formation is non-monotonic with mass. And these strip stars form different black holes compared to single stars, and the stars that will form black holes will not be the same ones. And now we come back to the black hole mergers. As I told you before, if you look at isolated binary stars, the stars that form black holes are these strip stars, right? And now we have seen that these strip stars will form different types of black holes. So if we look at the distribution of black hole masses that come from single stars, we can see a whole range of black hole masses. Here on the left at solar metallicity, and on the right at a much lower metallicity, which is 10 times less. And we can see that the whole range of black holes that we expect is completely shifted. If we do the same thing for strip stars, we can find something incredibly exciting. And that is that these black holes that we form are always at characteristic masses. So we find black holes when we have these compactness peaks, or these peaks in iron core mass I was talking to you about before. And they are typically at around 9 solar masses and at around 15 solar masses at solar metallicity. And if we go to lower metallicity, stars lose less of their envelopes because the winds are weaker. And that means that you can form a larger range of black holes. But the fun part is that the places, like the parts where we expect black holes to form most, are the same. What does that mean? It means that we expect that strip stars form black holes of universal masses. Universal, okay? So that means that if you look at a big population of black holes, we should always see them line up at the same masses if they come from these strip stars. And if you make predictions now for the binary black hole population, so where we pair up these black holes at lower masses or at higher masses, we can have a pair of 2 low mass black holes, or a pair of 2 high mass black holes, or a pair of a high mass black hole and a low mass black hole. So these peaks I was showing you before. And it turns out that from isolated binary evolution, this process of pairing a low mass black hole with a high mass black hole is actually quite unlikely. And so what we expect from our theory is that you would have a peak of 2 low mass black holes at around 8 to 9 solar masses in terms of chirp mass, and then a whole distribution of higher mass black holes above. And in between, you should not have many black holes. It's very unlikely. And so it's really exciting because it seems to line up with the distribution of black holes found by LIGO. And our interpretation is that we can directly connect it to which stars form black holes in binaries and why they form black holes at these masses. So this is an exciting prediction because, of course, we will know by the end of the summer if this holds, if there is something else out there. But in general, this has a number of consequences. Because if we get to observe this, and this is confirmed, it gives us a way to connect black holes back to stars. And then we can constrain unknown processes in stellar evolution. And we can even do cosmology. So basically, our models predict that it's much less likely to form binary black holes and also black hole neutron stars than other models have predicted in the past, because we take these islands of black hole formation into account. And what is fun is that if you see universal masses, if it's true that black holes tend to line up at 9 solar masses, then in principle you could use this for cosmology. Because from gravitational wave observations, you also get something like luminosity distance to the sources. And if you have a feature that is repeated across redshift at always the same mass, well, that gives you a standard siren, right? That gives you a way to measure the expansion of the universe. So if it's there, that would be very exciting. And the other thing that I find really remarkable is that the black holes that have been observed in the nearby universe also seem to be around 9 solar masses. So are they linked? Are these from the same progenitors? We don't know, but it would be really fun to investigate. So this is where I come to my conclusions. So if there's one thing I'd like to remember from my talk, it is that binary mass transfer really matters for the lives, for the death, but also for the afterlives of stars. And we can actually understand why, or like from the stellar evolution perspective, why stars are prone to forming black holes for certain core properties. And we know that black hole formation is actually not monotonic with mass. And based on the existence of these islands of black hole formation, we predict that the distribution of black hole masses should be bimodal, and we should have universal black hole masses that line up at something like 9 and 16 solar masses. And so far, our models seem to agree with gravitational wave observations, but future is bright. We'll find out if we need to revise our theories or if we can learn something about stellar physics from there. It has also vast implications and potential for cosmology. So thank you very much.